Hello student, good morning. I am Dr.A.K Sinha, Professor of Chemistry. Today I am going to discuss electrical properties. Last class I have discussed imperfection in solids. Now I am going to discuss electrical properties. Solids exhibit an amazing range of electrical conductivities, extending over 27 orders of magnetic range from 10 to the power minus 20 to 10 to the power 7 per ohm per meter. Solids exhibits amazing range of electrical conductance, extending over 27 orders of magnitude, ranging from 10 to the power minus 20 to 10 to the power 7 per ohm per meter. Solids can be classified into three types on the basis of their conductivities. First, conductor. Second, insulators. Third, semiconductors. Now come to the conductors. The solids with conductivity ranging from 10 to the power 4 to 10 to the power 7 per ohm per meter are called conductors. Metals have conductivities in the order of 10 to the power 7 per ohm per meter are good conductors. This is about conductors. Now, what about insulators? These are the solids with a very low conductivities, ranging from 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. And third one, semiconductors. These are the solids with conductivities in the intermediate range from 10 to the power minus 6 to 10 to the power 4 per ohm per meter. 10 to the power minus 6 to 10 to the power 4 per ohm per meter. Now I am going to discuss about conduction of electricity in metals. Conduction of electricity in metals. A conductor may conduct electricity through movement of electrons or ions. Conductors conduct electricity through movement of electrons or ions. Metallic conductors belong to the first category, that is the movement of electrons, and electrolytes to the second category, that is the ions. Metallic conductors belong to the first category, that is the movement of electrons, and electrolytes the second category, that is the ions, because when we dissolve electrolytes like NaCl, KCl, then it conducts electricity, okay, because they have charge, positive charge, negative charge. Metals conduct electricity in solid as well as molten state, not in liquid. Metals conduct electricity in solid as well as molten state. The conductivity of metals depend upon the number of valence electrons available per atom. Valence electrons available per atom. The atomic orbitals of metal atoms, atomic orbitals, okay, you know atomic orbitals. Atomic orbitals is the, you can say, place where there is a maximum possibility of finding an electron. Orbital is the space, three-dimensional space in which there is a maximum possibility of finding an electron. The atomic orbitals of metal atoms form molecular orbitals which are so close in energy to each other as to form a band. B-A-N-D, band means atomic orbitals, many atomic orbitals, they form molecular orbitals because their energy levels are very close, and that is called band. Okay, these atomic orbitals, many atomic orbitals form molecular orbitals because their energy levels are very close to each other. If this band, this actually molecular orbitals, when they will come close, then they will form band, B-A-N-D, band. In this band, if this band is partially filled, band may be completely filled, partially filled, or you can say not filled also. Okay, these three may is possibility: partially filled, completely filled, not filled. Then if this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then electrons can flow easily under an applied electric field and the metal shows conductivity. Here I use the one term unoccupied conduction band. Means here it is also a band, but here in this band electrons will be not there, just like a empty. Okay, then this band, in this band electrons are not there, that's why it is called unoccupied conduction band, unoccupied. And this, due to this unoccupied conduction band, if it will overlaps, if this unoccupied conduction band overlaps with a higher energy, means just a conduction band. There are two types of band I told you: conduction band and unoccupied conduction band. Then if band is partially filled or it overlaps with a higher energy unoccupied conduction band, means this band, unoccupied conduction bands, have higher energy. Okay, but there is no electron, then electrons can flow easily under an applied electric field and the metal shows conductivity. In metal both are possible, conduction band or unoccupied conduction band. Then electron will flow from this conduction band to unoccupied conduction band. If the gap between actually if I told you it is overlapping, means they are touching, they are very close, touching. Okay, this overlapping means that they are very close, they are touching to each other. Then here conduction will take place. means this type of metal show conduction, metal show conductivity or conduction. If the gap between field valence band, now you can say condition, if the gap between field valence band and the next higher unoccupied band, that is also called conduction band, is large. Now both are not overlapping, they are making some distance, gap is there. Then what will happen? If the gap between field valence band and the next higher unoccupied band, which is also called conduction band, is large, electrons cannot jump. Actually, generally electron will not flow like water. Okay, it jumps. Then here electrons cannot jump to it, and such a substance has very small conductivity, and it behaves as an insulator. When there is a gap between the conduction band and unoccupied band, means between the conduction band and unoccupied band, okay, the gap is there, then that is called insulator, because electrons can't jump to this unoccupied band. Okay, then field valence band and conduction band, that is also called unoccupied band. The gap is there, that's why it can't jump, and this conduction will be, you can say, very small conductivity, and it behaves as an insulator. Okay, now I am going to discuss conduction of electricity in semiconductor. Okay, this is very important. Okay, conduction of electricity in semiconductor. In case of semiconductors, the gap between the valence band and conduction band is small. Therefore, some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature, since more electrons can jump to the conduction band. Substances like silicon and germanium show this type of behavior. Silicon and germanium, question is asked, and silicon and germanium show this type of behavior and are called intrinsic semiconductor. Intrinsic, INTRINSIC, intrinsic semiconductors. Name itself is a semi, means not full conduction it will do. It will conduct, I can say less. It will show some conductivity, not you can say full conductivity, some conductivity. Slow, you can tell. And this is called, this type of you can say conduction means slow or some conductivity only it will show. Some electrons only may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature, since more electrons can jump to the conduction band. Substances like I told you, example silicon and germanium, show this type of behavior and are called intrinsic semiconductors. The conductivity of these intrinsic semiconductor is too low, very low, to be a practical use. Means so less that it will not of practical use. Then why semiconductors are in demand? When it is not of practical use, semiconductors, then why nowadays everywhere in these semiconductors are in demand? Then now you understand. This is means conductance is semiconductor is too low to be of practical use. The conductivity of this intrinsic semiconductor is too low to be of practical use. Then how we are making it useful? That now you try to understand. Their conductivity is increased by adding an appropriate amount of suitable impurity. Means here in this semiconductors, if you mix some suitable, you can say, impurity, then its conductivity can be increased. Their conductivity is increased by adding an appropriate amount of suitable impurity, and this process is called what is called doping. DOPING. This process is called doping. Doping can be done. How we will do the doping? In a simple way, you can tell mixing, but correct term is doping. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductors. As for example, silicon or germanium, these are the semiconductors. Then here doping can be done with an impurities which is two cases, which is first maybe electron rich or second electron deficient. That impurity should be either electron rich or electron deficient as compared to the intrinsic semiconductors. Such impurities introduces this impurities, what it will do? Such impurities introduce electronic defects to them. Okay, this impurities introduces electric defects. Then there are two types I told you, this doping material, doping impurities. First is I told you electron rich impurities. How it will work, that I am telling you. Okay, electron rich, I will come to both, but first I want to tell you electron rich impurities. Silicon and germanium belongs to group 14 of the periodic table, that you know, and have 4 valence electron each. Means last orbit 4 electrons are there each. Means silicon also, germanium also. In their crystals, each atom forms 4 covalent bonds with its neighbors, you can tell, because 4 electrons are there. Total 8 is required, you know. There is a capacity of 8, but 4s are there. Hence, they can make a covalent bond. 4 covalent bond is possible. And generally, you know, then silicon will form 4 covalent SiCl4. This is common. SiCl4, silicon tetrachloride. Then this silicon or germanium, that they will make 4 covalent bonds, can make 4 covalent bonds with its neighbors. When doped with group 15, means 14 and 15, first to understand, when doped with group 15 element like phosphorus or arsenic, As, P phosphorus, As arsenic, when it is doped with a group 15 elements like phosphorus or arsenic, which contain 5 electrons. You know, phosphorus valence electron is 5, arsenic is also 5. All 15 groups have 5 valence electrons. Then what will happen? This 14 group has 4 valency, silicon and germanium as for example, and this 15th has 5 valency, phosphorus and arsenic. Then what will happen? These 5 valence electrons are there. Then as you can say, this I told you that phosphorus and arsenic has 5 valence electrons. They occupy sum of the lattice sites in silicon or germanium crystal. They will occupy this phosphorus or arsenic, which contain 5 valence electrons. They occupy some of the lattice sites in silicon or germanium. Okay, means this group 15 elements like phosphorus and arsenic, they have 5 electrons, and this silicon or germanium have 4. Then when both will come in contact, then this phosphorus or arsenic, whatever be, they occupy some of the lattice sites in silicon or germanium crystal. Then 1 electron is remaining, 1 electron of phosphorus or arsenic is remaining. Out of means 5, 4 out of 5 electrons are used in the formation of 4 covalent bonds with 4 neighboring silicon atoms. The 5th electron is extra and becomes delocalized. Delocalized means they can move. This 5th electron is extra and becomes delocalized. These delocalized electrons increase the conductivity of doped silicon, because you know that movement of electron for the conductivity, movement of electron is responsible. So now 1 electron is there, this delocalized electron. Then many, you can say, this type of atom will be there, not only 1 atom, 1 or 2 atoms, many atoms will be there. Then many electrons will be there in the this doped material. In the doped silicon, many electrons will be there from either phosphorus or arsenic. Then due to this delocalized electrons, or you can tell these delocalized electrons increase the conductivity of doped silicon or germanium. Here the increase in conductivity is due to the negatively charged electron. Electron, you know, that is negatively charged. Hence, increase in conductivity is due to the negatively charged electrons. Hence, silicon doped with electron-rich impurity is called N-type semiconductor. N means negative. N-type, small n dash, N-type semiconductors. Now I am discussing, going to discuss electron deficient. Yes, reverse of these things. Electron rich. Now here is a electron deficient impurities. Silicon or germanium can also be doped. Silicon or germanium can also be doped with a group 13 elements. Group 13 elements is also useful. Can be that elements can also be doped with 14 means silicon and germanium. 13 also like boron, aluminum, gallium, boron B, aluminum Al, or Ga, gallium, which contains only 3 valence electrons. Only 3 are there. In 13 group, 3 electrons will be there, outermost orbit. Okay. The place where the 4th valence electron is missing. Now you can see in 13, only 3 electrons are there, 4th is missing. No, in 4th valence there is no electron. The place where the 4th valence electron is missing is called electron hole. Okay. The place where the 4th valence electron is missing, no electron, that is called electron hole or electron vacancy. Actually, I will send some diagrams, okay, for all the things. An electron from a neighboring atom can come and fill the electrical hole. This is important things. An electron from a neighboring atom can come and fill the electron hole, but in doing so, it would leave an electron hole in its original position. Means one will go from one place, it will go to the other. Then that will be vacant. From where this electron went to fill that vacancy, that valence it will give to the others. Then from the original there will be again hole. It will create one more hole. From one element one electron will go to the other. Then here it is going to fill others. Then there will create new hole, new electron hole it will create, and that will be of positive character. Okay. Then this I told you that it would leave the electron hole at the original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of its electron that filled it. Okay, that filled it, opposite direction. Again I am telling you, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes. Here, now if you will apply under the influence of electric field, electrons would move towards the positively charged plate through electronic holes, but it would appear as if electron holes are positively charged and are moving towards a negatively charged plate. This type of semiconductors are called p-type semiconductors. P means positive. I told you that whole electron will move from one place to the other. It is going to give to others, but original from where it moved, there it will be hole. That will be a positive character, and when electric field will be applied, then this positive charge, positive hole will move to the negative plate, negative electrode, and electron will move towards positive plate, positive electrode. Okay, Then see, two types of charge is created. Electron is moving towards positive electrode, and this positive electron hole, that is positive, that will move to the negative electrode. Then this type of semiconductors are called p-type semiconductors. Means p means positive, p dash type semiconductors, p-type semiconductors. I will try to send some diagram. Okay. Now I am going to discuss applications. What are the applications of n-type or p-type semiconductors? This is very, very important. Actually, all things what I am discussing today, I have discussed, is important for all type of examination. All type of examination, medical, engineering, UPSC, okay, everywhere, any competitive examination, this type of questions are asked. And now applications of n-type and p-type semiconductors. Various combination of n-type and p-type semiconductors are used for making electronic components. Actually, many times people will ask, what is the role of chemistry in computer science, or ECE branch, electronic and this electrical and electronics communication. These are the branches of engineering course. ECE, electrical engineering, and particularly computer science, and ECE, electrical and communication engineering. People generally, they will ask, those who don't know in details, role of chemistry in computer science. Now you should know. If you are knowing, then okay. If you are not knowing, then you should know. If these silicons or germaniums or like gallium, I told you, if these things are not available, already I discussed many examples, like aluminum also, gallium also, boron also, germanium, silicon. If these metals are not there, then computers will not work at all. Computer will not work at all. It will be useless. No computer science, no computer engineering, no laptop, no mobile. You can just understand the value of, you can say, these chemistry, or you can tell chemistry and these semiconductors. Due to these semiconductors, now all over the world, computers are working, laptops are working, mobiles are working, because they use transistor they will use, even in radio also, transistor, and chips, in computer chips they will use, CHIPS, chips, that is made from this material. Then now you can understand the value, because not all, few people, engineers particularly, they will question sometimes what is the role of chemistry in computer science engineering and ECE branch. Now I have told you it's a application, huge. Okay, even in electricity bulb, another thing, different type of bulb, and LED bulb, another things, diode is they are using, diode. Then now you can understand the value of chemistry in this field. After knowing, they will understand value, but many people does not know, particularly other branch engineers, they don't know, particularly computer science. Computer science somewhat they will know, but because they belong, they are studying physics and chemistry also, they know their background is there. But those who are not studied, they don't know that it has a major role in today's technology. This is the backbone. Without that, there is no existence of computer science. And if there is no computer science engineering, then you can understand how we will go, how back only you can imagine. Okay. Then now I am telling you applications of N-type or P-type semiconductors. Various combination of N-type and P-type semiconductors are used for making electronic components. Diode is a combination of N-type and P-type semiconductors and is used as a rectifier. Transistors are made by sandwiching a layer of one type of semiconductors between two types of other types of semiconductors. Transistors, what is a transistor? Now understand. Transistors are made by sandwiching a layer of one type of semiconductor between the two layers of other type of semiconductors. Like as for example, NPN means N-type, between the two N-type, in the middle P-type will be there. P-type semiconductor will be used between N-type semiconductor. NPN, what you are telling? NPN, between the two N-type semiconductors, P-type semiconductor will be used in transistors. And also PNP means between the two P semiconductors, one N P semiconductor will be used. Then NPN and NPN type and PNP type of transistors are used to detect or amplify radio or audio signals. Now you can understand the value. These transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode. Solar cell is an efficient photodiode used for conversion of light energy into electrical energy. Nowadays, everywhere you will find on the road at high poles, you will see that light in the night, that is this only solar energy is converted to electrical energy. Solar that is called solar cell. Solar cell, just like in torch battery we are using chemical energy, you are using like that way photo means light energy is converted to electrical energy by the use of this diode, okay, photodiode. Then here I have told you about application. Again further, germanium and silicon are group 14 elements and therefore have a characteristics valence of 4 valency. They have characteristic valence of 4 and form 4 bonds as in diamond. Just like diamond carbon has 4 valency, they are making like that way. Here also characteristics valency, 4 valency is there for silicon. Okay, but it is not making just like a diamond. Some limitation is there. A large variety of solid state materials have been prepared by combination of group 13 and 15. This 14, 15 already told you. 13, 15 also. 13, 15 or 12, 16. 13, 14 I told you and 14, 15 I told you. Now new thing 13, 15, one gap. 13, 15 and 12 and 16 to estimate average valence of 4 as in germanium or germanium or strontium, not strontium, germanium or silicon. Okay, to stimulate average valence of 4, because they want to make 4 valency all, that's why it is used. Typical compounds of group 13 and 15 are, I'm telling that combination 13 and 15. Then indium and antimony, first example, 13 and 15, indium and Sv, InSb, Sv means Sv, this indium and Sv, and second is aluminum and phosphorus. Sv means antimony, In indium and antimony, InSb. Second example, aluminum phosphorus, Alp. Third example, you can understand this, I told you this thing, aluminum phosphorus, and third example you can understand gallium and arsenic, gallium, GaAs, gallium arsenic, semiconductors, these are semiconductors, you know already are semiconductor, whatever I told all, you should know this name of this elements, semiconductor, all are semiconductors. And gallium arsenic semiconductors have very fast response and have revolutionized the design of semiconductors device. In semiconductor device, this gallium and arsenics are used. And this after that, again further I am telling you that this other example, this I will tell you, zinc sulfide and cadmium sulfide. Zinc sulfide, cadmium sulfide, and ZNS, CDS, and cadmium selenium, CDSE, and HgTe tellurium, Hg mercury, Te tellurium are examples of groups 12 and 16. Now you can see 3 gaps are there, 12 and 16, 13, 14, 15. Okay, 12 and 16. Then these are also used. These are the examples, means grouping is there. Zn and S. Okay, semiconductor will be used here. After that, cadmium and S, CDS, CDSE, and HgTe are examples of group 12 and 16 compounds. Okay, then I told you gallium and arsenide, GaAs, semiconductors have very fast response and have revolutionized the design of semiconductors device. And this ZnS, cadmium sulfide, cadmium selenium, mercury tellurium, HgTe are, these are the examples of group 12 and between group 12 and 16, 12-16 grouping. Okay, compounds. In these compounds, the bonds are not perfectly covalent. Again, important things. These compounds, ZnS, cadmium sulfide, last class also I have discussed about this imperfectness. In that I have discussed ZnS, cadmium sulfide, cadmium selenium, mercury tellurium. In this compound, the bonds are not perfectly covalent. And the ionic characters depend on the electronegativities of two elements. They are ionic, okay, not perfectly covalent, they have ionic character also. Ionic character depends on the electronegativities of the two elements. It is interesting to learn that transition metal oxides show marked differences in electrical properties. Here again important things are there. Transition metal oxide show marked differences in electrical properties. As for example, titanium oxide, TiO, titanium oxide, chromium oxide means CrO2, and rhenium oxide, ReO3. These three example I am telling you: titanium oxide, CrO2, chromium oxide, or rhenium oxide, ReO3, behave like metals. They are oxides. These are oxides, but they will behave like metals. Important questions for, you can say, advanced level, engineering advanced level competition. This type of questions are asking. Titanium oxide, CrO2 and ReO3 behaves like metals. Rhenium oxide is like metallic copper. See, again very important question. Rhenium oxide, ReO3, is like metallic copper in its conductivity, in terms of conductivities and appearance. It will look like copper in two terms, not in all, in the term of conductivity and in appearance. Certain other oxides like vanadium oxide, VO, VO2, VO3, and titanium oxide, TiO3, VO, vanadium oxide, vanadium dioxide, vanadium trioxide, and titanium oxide, TiO2, show metallic or insulating properties depending on temperature. They will show both. They show metallic or insulating properties. Both characteristics can show. That depends on temperature. This question is also asked. Okay. If you are attending the class, then you must keep a paper and pen so that important things you can write. Okay. This I have discussed about the applications. Now I am going to discuss metallic properties. Okay. This is also very important. All things are very important. Question is asked from every chapter. Some certain question is fixed. That in that number question will be asked. Then these things what I am highlighting, you should not forget. You should note down or you keep in your mind. Okay, better you sometimes note down important things. Then now metallic properties. I am going to discuss metallic properties. Every substance has some magnetic properties associated with it. Every substance. Here important things. Every substance has some magnetic properties associated with it. The origin of these properties lies in electrons. Electron is responsible for magnetic properties. Each electron in an atom behaves like a teeny magnet or tiny magnet, you can tell. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motion. Electron has two types of motion. Okay, first it's orbital motion around the nucleus. They will be moving around the nucleus. Then that is one is the orbital motion. And second, it's a spin around its own axis. It will spin also. Just a spin, you know, that in cricket ball they will spin. Means left side also, right side also, clockwise, anti-clockwise, like that, you know, that electrons moves. Then second I told you, a spin around its own axis. Then these two types of motions will be there. Electron will have these two type of motion. Means magnetic moment. Actually it is related to somewhat direction also. Magnetic moment originates from two types of motion. First it's orbital motion around the nucleus, and second it's a spin around its own axis. Electron being a charged particle, all of you know electron has charged. Electron being a charged particle and undergoing these motions can be considered as a small loop of current, which possesses magnetic moment. Thus, each electron has a permanent spin and orbital magnetic moment associated with it. These things you understand or keep in your mind. Each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very small, and is measured in the unit called Bohr magnet, BR, Bohr magnet. Okay, BM, not a BM, Bohr magnet, shortcut, BM, Bohr magnet. It is, and what is its value? Bohr magnet, then it is equal to 9.27 into 10 to the power minus 24 am square, a ammeter meter square. Okay, not this 24, 34. Okay, 9.27 into 10 to the power minus 34 am square. Okay, ammeter meter square. On the basis of their magnetic properties, substances can be classified into 5 categories. All categories are very, very important. Just listen what are the 5 categories. First is paramagnetic. Second is diamagnetic. Third is ferromagnetic. Fourth is antiferromagnetic. And fifth is ferrimagnetic. Ferry. Last is, fifth is ferrimagnetic. These are the, you can say, 5 substances on the basis of their magnetic properties. Then now one by one I will discuss. And all 5 are asked in examination. First, paramagnetism. You might be knowing also. Paramagnetic substances are weakly attracted by a magnetic field. It can be magnetized also. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. It can be magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. If you remove the magnetic field, then its magnetism will go. Okay. They lose their magnetism in the absence of magnetic field. Question is asked here. Paramagnetism is due to presence of one or more unpaired electrons which are attracted by the magnetic field. This question is also asked. Paramagnetism is due to the presence of one or more unpaired electrons, which these electrons are attracted by the magnetic field. What are the examples? Examples also you should know. Examples also they are asking. Then oxygen, O2, cupric oxide means Cu2 plus, Fe3 plus, okay, Fe3 plus, Cr3 plus. This I told the 4 example. Oxygen is paramagnetic, cupric ion is paramagnetic, ferric ion is paramagnetic, chromic ion is paramagnetic. Again I am telling O2, Cu2 plus, Fe3 plus, Cr3 plus are, you can say, some examples of such substances. Question is asked, or they will give in option, one correct answer will be there, other 4 they will write other, you can say, other substance which are not paramagnetic. Hence, these questions are important. Now I am going to discuss diamagnetism. Already this also might be knowing. It is repelled by the magnetic field, no attraction. Diamagnetic, understood? Diamagnetism, what is this? Then diamagnetic substances are weakly repelled by a magnetic field. What are the examples? Then 3 examples I am telling you. H2O, water, liquid water, NaCl, sodium chloride. NaCl means sodium chloride, and benzene, C6H6, benzene. These are actually diamagnetic. Water actually, it is a very weak current can pass through it, but it is very weak, feebly, very less. But here, these are coming under the diamagnetism. H2O, NaCl and benzene means C6H6 are examples of such substances. Here further they are weakly magnetized in a magnetic field in opposite direction. If it will magnetize, it will magnetize in opposite direction, weakly magnetized in opposite direction. Diamagnetism is shown by those substances in which all the electrons are paired. All electrons are paired and there are no unpaired electrons. Means you might have seen electron that up they will arrange arrow will be one electron upside, means arrow will be up, other will be down. Then both will neutralize, both electrons will be neutralized to each other. One will be clockwise, other will be anti-clockwise, up, down. Correct? It will be like that. One electron, half arrow will be up, other electron, half arrow will be down. Then both will cancel the effect. Hence, here electrons are paired. Electrons are paired. That's why both will cancel their effect. Electrons are paired and there are no unpaired electrons. No unpaired electrons. That is the sign of diamagnetism. When you write electronic configuration, that time quickly by seeing this electron situation, how electrons are there, whether it is paired or unpaired, you can tell. If unpaired means paramagnetic. If it is a paired, no unpaired is there, only pairs are there, then diamagnetism. Question is asked. Pairing of electrons cancel their magnetic moment and they lose their magnetic character. Now I am telling you these things. Ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium and chromium oxide. These are the example, keep in mind or note down. Iron, cobalt, nickel, gadolinium and chromium oxide, CrO2, are attracted very strongly by a magnetic field. Such substances are called ferromagnetic substance. Besides a strong attraction, these substances can be permanently magnetized. In solid state, the metal ions of ferromagnetic substances are grouped together into a small regions. All ions in solid state, the metal ions of ferromagnetic substances are grouped together into a small region. That region is called domains. DOMAINS. Okay, grouped together. Ions are grouped together, then that region is called domains. Thus, each domain acts as a tiny magnet. TINY, tiny magnet, each domain. acts as a tiny magnet. In an unmagnetized piece of, here important things, that here in an unmagnetized piece of unmagnetized substance, unmagnetized piece of ferromagnetic substance, the domains are randomly oriented, not in a proper way. Means some are up direction, others are down, randomly, not in a proper way. When it is unmagnetized, no, they are not in a proper direction, they are not arranged in a proper direction. In unmagnetized, when they are unmagnetized, okay, when the substance is placed in a magnetic field, then what will happen? All the domains get oriented in the direction of the magnetic field. In the same direction, all will be oriented. That's why it behave like a magnet, and a strong magnetic effect is permanent. And this magnet will be a strong magnetic effect. This magnetic effect generated or developed is produced. Okay, this is a strong magnetic field is produced when you will keep in magnetic field. This ordering of domains persist even when the magnetic field is removed. This is important thing. First case you have seen, after removing the magnetic field, that magnetic effect was going, magnetic property was going. But here, even when removed magnetic field, the magnetic field is, when it is removed, then this will be there, magnetic property will be there. Okay, the ordering of domains persist even when the magnetic field is removed, and the ferromagnetic substances becomes a permanent magnet. Now anti, then just opposite of this, anti-ferromagnetism. Substances like manganese oxide, MnO, showing anti-magnetism. manganese oxide, MnO, showing anti-ferromagnetism, have domain structure similar to ferromagnetic substance. Same type of structures, means when they are not magnetized, then same type of structure will be there, like a ferromagnetic, means not in a proper way it is arranged, but their domains are oppositely oriented. Here substances like MnO, manganese dioxide, showing anti-ferromagnetism, have domain structure similar to ferromagnetic substances, but their domains are oppositely oriented, means one up, other down, but not in an equal number. Somewhere, in some places it is a up direction, other is a low direction, down direction, like that way oriented. That is called oriented, but their domains are oppositely oriented, up down like that, and cancel out each other's magnetic moment. That's why it is called antiferromagnetism. Okay, no magnet, even the magnetic properties can't be generated. Okay, antiferromagnetism. Last is ferromagnetism. Then here, what is the ferromagnetism? First understand, ferromagnetism is observed when the magnetic moments of the domains in the substance is aligned in parallel and anti-parallel direction. Parallel direction means up direction. What parallel means, you know that both electrons are in the same direction, that is called parallel. When they are in opposite, then it is called unparallel. Okay, parallel directions or anti-parallel also you can say. When they are not in a parallel, it is called anti-parallel direction, then they will be in unequal number. Okay, here electrons arrangement, I am telling parallel or anti-parallel. Sometimes it will be in parallel, some electrons will be in parallel, some electrons will be anti-parallel direction in unequal numbers, not in equal number, unequal number, and these are weakly attracted by magnetic field, weakly attracted by magnetic field as compared to ferromagnetic substance. What is the example? Then Fe3O4. Ferromagnetism example is Fe3O4. It is less, I told you, weakly attracted by magnetic field as compared to ferromagnetic substance. What is example of ferromagnetic substance? Then Fe3O4. This is also called magnetite, Fe3O4. Other example is ferrites. Examples like Mg-Fe3O4. Magnesium is there attached. Mg-Fe3O4. It is called ferrites. And other example is Zn is attached with Fe3O4. Then Fe2O4. Fe2O4. Actually, first is Fe3O4, magnetite, and ferrite is Mg-Fe2O4, not 3, Fe2O4, and other is Zn is there, same composition, Zn Fe2O4. These example I told you for ferromagnetic substance. Fe3O4 first, second is ferrites. Then there are two examples I told you, Mg-Fe2O4 and Zn-Fe2O4. These are examples of such substances. These substances also lose ferromagnetism on heating and becomes paramagnetic. Her plus point is there. These substances also lose ferromagnetism. It will lose, and one positive thing will happen, ferromagnetism it will lose and becomes paramagnetic it will become. Okay, after losing ferromagnetism on heating, it becomes paramagnetic. Okay, then this I have discussed these things, all magnetic properties. Now this chapter solid state is finished completely, and next class I will start new chapter. Thank you.